This is a production of Cornell University.
So, so it's a pretty broad topic. And I'm going to present a piece of it that we've been working on. And by we, I mean there's been a group of us, and it really is a group effort. And that's myself, Liz Carter, Susan Rhea, and Steve Shaw, with input from Peter Woodbury. And I should say that there are several groups around the world that are really doing great work in this area. We had a seminar a couple weeks ago from a person from Australia, Scott Chapman, who is with CSIRO, and he's associated with a group at University of Queensland that is really doing great work on trying to help agricultural producers in Australia deal with impacts of climate, and that's important there. And so why maize, why climate impacts, and how do we get involved? So the kind of global answer to the first question is maize is a big crop. It's the leading cereal crop in the world. Demand's supposed to increase by 50% over the next 50 or 75 years. And over that time, temperatures are supposed to be increasing by at least 2 or 3 degrees C, potentially. So that's kind of the overarching reason. And why climate impacts? Because we're expecting these increases in temperature, and we don't potentially changes in precipitation. There's been a number of papers over the past 10 years, primarily from folks who are not, their primary area is not agriculture, where they have done yield projections using statistical modeling, and they've suggested pretty severe impacts of increasing temperatures on maize productivity, both historically but also in particular into the future. Several years ago, Susan and Steve kind of looked into this and had some questions about the methodologies and results. And that led to a paper where they did some initial work on looking at irrigated maize production to see whether they could detect a temperature impact on irrigated maize. And they were unable to in the data they looked at. But that led to a Hatch proposal that was funded and allowed us to look more intensively at the impact of climate on maize, with particular emphasis on temperature, but it kind of evolved into additional impacts. So I'm just going to try to go through some of the kind of climate impacts on maize yields. So the cap on yields is solar radiation. So I don't have that here, but that at any given location for any given soil is going to be solar radiation. But the next most important impact, despite all the emphasis on temperature, actually is precipitation. I think most agronomists and crop physiologists would agree that that's the main limitation, climate limitation on maize production. So I got this quote from Tom Sinclair, the 1,000-pound gorilla in crop response to climate change. He's referring to precipitation. That's partly because, maybe to emphasize that, it's precipitation more than the more recent emphasis on temperature, but also the fact that projections of precipitation are really uncertain. So we really don't know what's going to happen. That's going to have a major impact. But there are direct temperature impacts on maize, and probably the most well documented is on phenology. That means higher temperatures, accelerated rate of development, reduced cumulative intercepted radiation, and lower yields. And that's been pretty well documented. There also are physiological impacts, reduced pollen viability, loss of membrane integrity, inactivation of some heat-sensitive enzymes, particularly in photosynthesis and in starch synthesis, and increased respiration. But those, at the temperature, it's 38 to 40 degrees C, and keep that in mind because we'll be coming back to that in a bit. There are what have been proposed these indirect temperature impacts, and primarily that there's going to be an increase in evaporative demand. It's going to cause more frequent bouts of water stress in maize and reduce yields. I'm going to actually spend a fair amount of time on that, and I'll get back to that in a bit. There are complications, and that's these interactions. For climate, the problem is that high temperature, drought, high evaporative demand are all highly correlated. They often, at least in the U.S. Corn Belt, they occur all at the same time. So it becomes very difficult then to isolate which are the factors that are most responsible for impacts on yield. And that's something that Liz has been wrestling with quite a bit recently. The second thing, and I'm not going to really talk about this, but it's, I think, pretty important, is there's not really clear information on when maize is under water stress, how will higher temperatures impact yield? In other words, what kind of interaction is there when the crop is already in stress from one, say drought? How will then elevated temperatures have, and what additional impact will they have? And that's it's something that there's not a lot of literature on, and the literature that's there is not real clear on that. But it's important because it'll give information on what are the impacts on the thresholds for damage from, say, temperature or water stress. So just to kind of do a very simple, very brief kind of overview of my sense of the literature, the more recent literature that I mentioned on statistical modeling is there was first an early focus on temperature. And this was in precipitation or drought was considered secondary in these studies. And they reported pretty significant impacts, both historically and in projected into the future, as I mentioned. But note the thresholds that they were using to where they expected damage to occur, reduced yields, was around 30 degrees C. That's in contrast to what we saw before for the physiological damage. More recently, I think as they became associated with more agriculturally oriented people, let's say, they shifted their emphasis to that the impact of higher temperatures, climate change, was going to be by increasing evaporative demand, as I mentioned before. And this is something where, again, they're projecting pretty significant impacts. And I'm going to try to get to this and explain it a little bit better, and I hope I'll be able to do that because we have some questions about that. Also, in these more recent kind of statistical studies, they've understood that there's acclimation that occurs in maize to high temperatures that could modify or mitigate the impact of temperature. There's also, one has to account for genetics, management, and soil factors, and that there are impacts by growth stage. These genetic, management, and soil factors are really important because they not only impact yield independently of climate, but they interact with climate to affect maize yields. And another quote from Sinclair, which I thought was quite good, is right here: temperature increase imposed on current crop systems without management or genetic changes is often predicted to decrease yields, but it is highly likely that cropping systems will remain static. And I think I'll be able to show some data. It's often predicted, but it's highly, well, he was saying that they'll remain static. The yields won't be affected. The temperature, they're projecting decrease. Actually, I'm glad you brought that up, Peter, because actually I think we can show, at least in some of our data, that management can actually increase yields, even with increases in temperature. So I'm just going to go through a series of questions and to try to address this and the climate impacts. And this one on the VPDs, I just wanted to say right now there's two aspects to this impact of VPD on maize yields or increase evaporative demand. One is whether there actually will be an increase into the future in the U.S. Corn Belt. And the second is how, if there is, what is the interaction between VPD and the processes of interest? That would be evapotranspiration and carbon assimilation in maize. So I'm going to try to get to that, and hopefully it will be a little clearer. So this first question we address by using statistical modeling of both irrigated and rain-fed maize yields. And I'll get to that in just a second. That's work that Liz has been primarily involved with, and in fact gave a seminar last spring on the irrigated component of that. So the advantage we had here is we had access to a data set from the National Corn Growers Association for both irrigated and rain-fed categories or classes. This was from 2005 to 2012. It was focused mainly in the Western Corn Belt, but in the rain-fed we included Iowa also. We have other additional states. We haven't started the analyses on those. This is under, so the advantage is it's optimal management. So the limitations on yield are going to be due to whatever the local factors like soils might be. But other than that, it's going to be a climate impact. And that's what we were really trying to get at, was what is the impact of climate. There were a large number of values, yield data that we had. And then we had, the real nice thing is we had all this additional information. So this is both management and genetics information that was really quite useful in trying to explain the impacts on maize yields, both in the irrigated and in the rain-fed data sets. And those were used to define growth stages that were used, we used to both look at seasonal impacts, but also impacts by growth stage. Again, Liz gave a seminar on the irrigated part of this work, and the main findings there is that there was evidence for acclimation. There was no impacts of temperature. Even in 2012, when we had near record or record temperatures across the U.S. Corn Belt. There was also evidence that by agronomically realistic adjustments of management, you could actually increase yields. So there was room for actually improved yields in the irrigated maize in the Corn Belt. So I'm not going to. So that's all I'm going to talk about for the irrigated, again, because that was been presented, and actually that work has been submitted for publications under review right now. So this is kind of a summary of the precipitation and grain yields over time for the rain-fed, and just for to contrast, I have the irrigated here. So the main thing to note with the precipitation is, pretty steady, but 2012 was a very, very low precip year. By mid-June or so, precip shut down, and there was very little after that, particularly in the Western Corn Belt. This was associated with very high temperatures and very high VPDs. I'll explain a bit more about that. No impact on the irrigated yields, like I just mentioned. In fact, 2012 was the highest yield, highest yielding year of the period that we looked at. And this period included, I didn't show the temperature data, but this period included quite a broad range of temperatures, so both higher and lower. The rain-fed yields are here. So you'll note, I think anybody who's aware, somewhat aware of grain yields will note that they're pretty high. So it's important to keep in mind this is a yield contest. So these growers are selecting their best sites. So even where there may be, precipitation, it may be getting to the edge of the kind of rain-fed production agriculture, they're still selecting very, very their best sites. So it's going to maybe shift the yields a little bit higher than what they would be normally. But in 2012, there was a reduction, and this reduction, the percentage reduction in yields in these yield contest data is pretty much the same as what the overall reduction in yields were in the Midwest in 2012. That's reported in the National Agricultural Statistics. So even though the absolute values are higher, the magnitude of reduction in 2012 was about the same. And I'm going to focus on 2012 because of the the climate extremes that occurred in that year. So this is kind of some summary data, and most of what I'm going to show is descriptive because we're still in the preliminary part of these analyses. The top panel is grain yield as a function of vapor pressure deficit. This is for rain-fed for Kansas, Missouri, and Nebraska. So you note that does appear to be a relationship whereby at higher VPDs you do get lower yields. Important to keep in mind, though, that there's correlations among the climate variables here, and we'll get to that. So it's not maybe so much of a surprise that the statistical modeling that's been done might show that VPD is a factor in impacting maize yields, but I think what we'll try to show is that it's much more complicated than that. We look at Iowa. Iowa's interesting. The rain-fed data, same thing, grain field as a function of vapor pressure deficit. There was really no impact, partly because the climate was not as severely impacted in 2012 as it was in the Western Corn Belt. So we never got the really high VPDs, low precip, and as high temperatures. This is the irrigated as a comparison. Shows that when you eliminate water stress, there's no impact of vapor pressure deficit or high temperature on yields. So getting to this correlation that I've been mentioning. So this is the kind of combined data for all the yield data for the rain-fed from 2005 to 2012, showing the season average Tmax as a function of season average vapor pressure deficit. And you can see clearly there's a relationship. The higher the temperature, the higher the vapor pressure deficit. There's a color code here for precip for June, July, and August, total precip. You'll note that the higher precips are at the lower VPDs, lower temperatures. As you get to these higher values, that's where the lower precipitation is occurring. So again, important to keep, this is important to note, so it makes it more difficult to identify these drivers. This is another way of looking at where we plotted grain yield as a function of growing season precipitation, where we color-coded for vapor pressure deficit here. So darker colors are higher vapor pressure deficits. So you note down to about 300 millimeters of June, July, August precip, yields are scattered, but they're all fairly high. But about 300 and lower, you get quite a range of yields, and you start getting some very low yields. These are in particular where the very highest vapor pressure deficits were recorded. This was interesting. These were interesting data because of the large range. And I'll try to explain why you might, at least is one factor that might be responsible for why you're getting very high yields but also very low yields here. But again, just pointing out this correlation among these climate factors that are important in determining maize productivity. So I was going to present some initial data on the statistical modeling that Liz has done, but I decided not to because I felt like I wasn't confident enough of my knowledge of that modeling to do that. But I did want to present one thing. First, to note that in the modeling that she's done so far, all the climate factors were significant. So VPD, precipitation, temperature, and the temperature thresholds that we looked at, the indices that we looked at, all came out to be having significant impact on maize yields. The biggest impact, though, interestingly enough, was planting rate. And my interpretation of that is that what it appeared to be is that in the yield contests, the growers were actually too conservative in their planting rate. What we found when we looked at the rain-fed data for the 4 states we looked at is that under all scenarios, under all vapor pressure deficits, you did better by increasing your planting rate. So you got higher yields no matter whether it was, no matter what VPD. I think, again, this comes back to the fact that in these contests, they're picking their best sites. So these sites are going to have a maximum water holding capacity, soil water holding capacity. And I think for 2012, in that year, they were just able to, they had enough stored soil water to produce a pretty good yield. That's my kind of interpretation, but we're still analyzing these data. But again, note that even at very high planting rates, that's where you got your maximum yield at all vapor pressure deficits. I should say that we're focused on rain-fed maize here in humid production, humid region production. This is not dryland production. Dryland production, the recommendations for planting rate are much lower than what we're showing here. In part, that's because the growers tend to be risk averse, but also the seed companies are predicting, or not predicting, but prescribing lower planting rates, in part because they don't want to have the onus of having a total crop failure. But that's not what we're talking about. We're talking about rain-fed, humid region production here. So a couple of the problems that Liz, she's settling on the appropriate methodology for variable selection and coefficient estimation or modeling, statistical modeling. The problem that she's had is a correlation that I just mentioned on the climate variables, but also that there's a spatial correlation between management and climate variables. And that's, Liz is, I think, getting to a point where we're close, right, Liz? It's been a long process, but she's done an excellent job on it. So I'll move on to the second question, which is, this gets back to the VPDs. Is there evidence to support this assumption of higher VPDs in the Corn Belt under climate change? Now, this is really out of my waters here, but this is what I'm understanding is occurring. The precipitation, most of the precipitation for the U.S. Corn Belt comes from systems coming out of the Gulf of Mexico. They come up the Mississippi Valley and they produce rainfall. When that doesn't, there are occasions though where you get these episodic droughts. This occurs when a high pressure system embeds in the Midwest. It blocks the transport of precipitation of these systems up from the Gulf of Mexico. And this has occurred in 1983, 1988, and then, as I've been talking quite a bit about, in 2012. The sequence of events is important here because what as far as I understand from the literature, the main instigator is reduced precipitation. So there's less rainfall. This reduces regional evapotranspiration. That means that more of the incoming soil aeration is getting partitioned to sensible heat, which atmospheric heating, let's say. Higher temperatures, and these higher temperatures lead to the higher vapor pressure deficits. So the real instigator is not that there are going to be higher vapor pressure deficits as a blanket, as a blanket statement for all future climates. It's only going to be during these episodic droughts, and the instigator is going to be reduced precipitation. It is unclear whether these episodic droughts events where you have these high pressure systems embedding in the region, whether they'll be more or less likely to occur with climate change. But I did think it was interesting that one of the candidates for the geospatial position, Nathan Mueller, in his work, the prediction was that they will not be more frequent. That, in fact, there's likely to be higher total precipitation during the growing season in the Midwest. But there's still some uncertainty about that. So with respect to whether there'll be higher VPDs, I think based on this, I would say it's not, if they are higher, they're not going to be significantly higher. And the only time you'll get them is during these episodic droughts. So then we'll move on to the kind of the third question is, what can we say about the impact of climate on key processes in maize? And for this, I'm going to move more into a little more in depth on the impact on the crop, and in particular focus on the diurnal dynamics of evapotranspiration in particular, not so much on carbon assimilation, although we did that, but look at diurnal dynamics at the field level of those processes in relation to temperature and vapor pressure deficits or evaporative demand. So the way I'm going to do that is by talking about work that we've done using flux tower data and eddy covariance methodology to look at fluxes of latent heat flux or evapotranspiration and sensible heat fluxes, in other words, heating, and then with additional data, look at some other things, including changes in canopy temperature, changes in aerodynamic conductance. I won't talk about that, but that's one of the key factors that is involved. But then, in particular, focus on canopy conductance as a function of these climate variables, diurnally and at the field level. We mainly focused on Ameriflux towers in Mead, Nebraska, and we looked at the irrigated maize towers, and I'll explain a little bit why we did that. We also had a tower in Aurora ourselves, in Aurora last year, which actually produced quite good data. I won't be getting to those data, just don't have time, so I'll focus mostly on the Mead data. So this is hopefully going to help set up a little bit of what I'm going to talk about. When we're talking about these fluxes, latent heat and sensible heat fluxes, the amount of energy coming into a field to the surface of the canopy is the described here as incoming solar minus reflected solar radiation plus the difference between long wave in and long wave out. We're calling that the net radiation. So that's total energy coming into the top of the canopy. That energy has to be dissipated somehow in order to balance the equation. It can either be lost as evapotranspiration or it can be lost as sensible heat. Sensible heat just means you have an object at a higher temperature and a lower temperature, and it's the energy transfer from the higher temperature to the lower temperature. When we're talking about a crop, it's almost always during sunlight hours, means the temperature of the canopy is higher and we're transferring energy from that canopy to a lower temperature atmosphere. So the way you can think of how the crop impacts this, so there are two factors that affect how this energy is partitioned between evapotranspiration and sensible heat loss. One is VPD, so that will affect it. Higher VPDs will shift it more towards evapotranspiration and less towards sensible heat loss. But the plant has control over that through crop conductance. So at higher crop conductances, you have the same effect, a shift towards more evapotranspiration under any given set of conditions. At lower crop conductances, in other words, like under water stress, you shift the energy is shifted more towards sensible heat loss. In other words, the canopy heats up. So I hope that helps a little bit when I talk in the next few slides. But another thing to note is that globally, about 80% of the net radiation is dissipated through evapotranspiration. So that when we're talking about increases in temperature, increases in evaporative demand, there's a limit set by the amount of incoming energy as to how much can be shifted, how much more evapotranspiration can occur. If you look at this example, if we're averaging around 6 millimeters per day of evapotranspiration, where 80%, and that represents 80% of the total net radiation. The most you can get, the most increase in that you can get is about to 7.5 millimeters per day. So there's a real limit. So it's not like you know, you just are capped by the incoming energy. So that's an important thing to keep in mind. So here's some kind of just to look at some of the diurnal dynamics in kind of broad terms. These are data from one of the Ameriflux towers at Mead, just showing a typical kind of diurnal sequence of changes. This kind of orangish bar is the incoming net radiation. The green is the evapotranspiration or latent heat. And the red is sensible heat. This is for a well-watered canopy. So you can see that most of the incoming net radiation is accounted for by evapotranspiration and very little by sensible heat transfer. One thing to note is that the blue dashed line is a vapor pressure deficit. So the key thing to note is that the highest vapor pressure deficits are actually occurring later in the day when net radiation is low, evapotranspiration is low. We'll come back to that in a bit. So this is a kind of a typical water stress canopy then. Same incoming net radiation, but because we're beginning to get stomatal closure or reduction in crop conductance, the shift in partitioning of that energy is now more to sensible heat and less to latent heat or less to evapotranspiration. So what's the impact? The impact is that we look at air temperature versus canopy temperature for that water stress example. We're now getting canopy temperatures that are significantly above air temperature. And I'll explain more about that a bit. So these are data from the Mead towers for irrigated maize for 2010, 11, and 12. So you might wonder why we're using irrigated data here when I'm talking about about rain-fed maize. It just so happened fortuitously for us, but maybe not for them so much, that in 2012 they basically weren't able to keep up with the irrigation. So they actually had essentially a deficit irrigation. They were getting water stress in their crop. And so that actually turned out nicely because we were not able to get rain-fed data from those towers in 2012. They were in a soybean maize rotation, and that year they happened to be in soybean for the rain-fed towers. So the first thing to note is, you know, what we see here is vapor pressure deficits over the course of the day. This is for the growing season. This is from canopy closure to the beginning of senescence. So it's time when there's a full canopy, but no senescence. These are the compiled data over that time for the different hours here. So the vapor pressure deficits remained fairly low during the 2 years where there was good irrigation. They were not drought years. During 2012, like we've been talking about, the vapor pressure deficits increased considerably, and again, we saw that earlier in some of the data that we showed for the yield contests. So this is interesting because this shows latent heat evapotranspiration as a fraction of net radiation over time for the same 3 years. So keep in mind, net radiation is approximately equal to latent heat plus sensible heat, or evapotranspiration plus sensible heat. So you can see through most of the day, we're at about 0.8. So that's about, as I was pointing out before, globally, about 80% of net radiation is accounted for by evapotranspiration, and so this is pretty consistent with this, and that occurred in all 3 years. But note, later in the day, this is when the VPDs are increasing. We do see an increase in all 3 years in the fraction of net radiation that's accounted for by evapotranspiration. And it goes up again in all 3 years. What was interesting is 2012. So in 2012, it actually went above, the ratio went above 1. So how can that be? Well, that happens because the canopy is actually being cooled to the point where there's now the sensible heat flux is reversed. You're actually getting heat transfer or energy transfer from the atmosphere to the canopy. The question is, from a kind of a production standpoint, with respect to these drought periods, is this a good thing? We're losing water here, and it's occurring at a time when net radiation is going down. There's not that much photosynthesis. Crop photosynthesis is actually declining pretty steeply then. What if we were able to stop this? Could we conserve water in these drought years and potentially, get a higher yield under those conditions? And I'll come back to that, but that's something to consider. So this shows the crop conductance, and it shows that, so this is a typical pattern that we see for well-watered crop conductance over the period of a day. So 2010, 2011, 2012 was lower. By the time crop canopy closure occurred in these fields, the drought was already in place. They were not keeping up with the irrigation. So we were already seeing evidence of that by lower crop conductances in 2012. So even though conductance is going down, you'd think would then reduce evapotranspiration. The very high VPDs that we saw earlier here were high enough to counteract that and create, actually result in this, where we were getting evapotranspiration at such a high rate that we were actually getting canopy cooling. So, and this shows what the kind of net result of that is that instead of that canopy being much higher than air temperature, than the temperatures that we see in the irrigated years, it actually was being maintained pretty close to those, and really not in a range where we'd expect any temperature impact. So is this a good thing? You might argue that it's better to keep temperatures, it's better to lose a little bit of water and keep those temperatures, canopy temperatures, a little cooler if your main concern is temperature. If your main concern is water, you might go the other way and say, well, let's have some more stomata closure. And we'll sacrifice a little higher temperatures, but we'll save some water. So this shows just kind of a summary graph where we're looking at evapotranspiration in millimeters per hour as a function of vapor pressure deficit. Color code's the same. We have blue for 2010, green for 2011, and red for 2012. So the thing to note here, and this gets back to how much total evapotranspiration can occur when you're capped by the amount of energy, limited by the amount of energy coming in. You can see that at about 2 kPa vapor pressure deficit, basically you can't transpire any more water. That's kind of it. You can see the impact of the lower conductance in 2012 in that at any given VPD, we're getting higher ET rates in 2010 and 2011. But you'll see at the highest VPDs, those are occurring in 2012, and we're seeing those out here. There's quite a scatter of points here, and I'll show this in a bit, but this is because net radiation is going down at the time the highest VPDs are occurring. And so you're actually getting, even though you're at a maximum or above, the evapotranspiration as a fraction of net radiation is actually above 1. The total amount of water loss is actually not that high. So now I'll get to the last question, which is this issue of what do you want to do in terms of trying to improve crops, improve maize hybrids for these episodic droughts. And what Pioneer has opted to do in their breeding is to come out with so-called drought-tolerant varieties. And those drought-tolerant varieties, it's clear that one of the traits that has been introduced is that they have made them sensitive to vapor pressure deficit. So above a certain vapor pressure deficit, the stomata begin to close. And the idea is you're conserving water during those drought years so that you have enough water to get a decent yield at the end of the growing season. And so I'm calling these kind of reduced transpiration hybrids. So they've opted for the water conservation and not for any impact that there might be as a result of that on temperature. So this shows some modeling results that were from a paper in Journal of Experimental Botany by the pioneer folks primarily, to try to demonstrate what the value of this trait might be. They have their drought tolerant and drought sensitive is the dash, looking at changes in soil moisture over the growing season. And you'll see that early on with this trait, reduced transpiration trait, there was less water extracted from the profile and more water towards the end of the growing season in the drought tolerant, quote, drought tolerant variety. When they looked at total biomass and yield in this modeling exercise, you'll see that up to a certain point, they were both the same, but then late in the season, because the more available water deeper in the soil profile with the drought tolerant, that variety was able to use that water and produce more yield and more total biomass. So what we did, just to kind of take a quick look at this, was we did a modeling exercise where we looked at York, Kansas in 2012, a very hot, very dry period. And we looked at two scenarios. One was where we had crop conductance independent of vapor pressure deficit, and one where we allowed it to be dependent on vapor pressure deficit based on data from a paper that was used as one of the kind of foundations for introducing this trait into these drought-tolerant varieties or sensitive, reduced transpiration varieties. So the first thing is the total amount of ET that occurred when it was independent was 217 millimeters over this month versus 182 millimeters when you had made this crop conductance dependent on VPD. So it does save water, at least based on our work here. If you look at evapotranspiration hourly as a function of vapor pressure deficit, we saw this just on a few slides previously, showing a kind of a cap around 2 kPa. What's interesting is the blue are before 3 p.m., the red are 1 to 3 p.m., and the green are after 3 p.m. So this just illustrates that even though the VPDs were very high later, the total amount of water loss was not as high as earlier because the net radiation was lower. So this is for where crop conductance is independent of vapor pressure deficit. Where it's dependent, we actually cap this at a lower ET rate, so at around 7 millimeters, 0.7 millimeters per hour. So we get the savings of water, and that's a good thing if you're in a drought situation and you want to you're willing to sacrifice maybe a little bit of yield in the really good years, but you're going to get more yield in the drier years. The problem is temperature. So in this scenario, we had air temperature. We looked at canopy temperature with no VPD dependence, and canopy temperature where there was a dependence of crop conductance on VPD. Got a little screwed up here, but the air temperature over that period, the maximum air temperature was around 37 C. No VPD dependence, the canopy temperature was around 38 degrees C. When you hadn't made a VPD dependent, you were saving water. The result was that you increase your canopy temperature. So the question is, what do you want? If you have this trait, you'll save water, but you're going to get higher canopy temperatures. You're going to start getting canopy temperatures presumably into the yes. What? Yep. Well, what they did when they looked at a large range of genotypes in this initial work that was done on this, and they just it was growth chamber work and looked at imposing different vapor pressure deficits, and at what point did they begin to get a shift in transpiration, indicating a sensitivity of stomata to vapor pressure deficit. A lot of genotypes didn't show that response, but there were some that did. So that kind of apparently was the foundation for moving to trying to include this trait into the hybrids. So again, you can save water, but you potentially are pushing canopy temperatures pretty high. A paper just recently came out in Crop Science where there was some recognition of the problem with this, and so what they've tried to identify, and they think they have identified, are hybrids that are sensitive to VPD. So they shut down or they reduce transpiration at higher VPDs, but at a certain temperature, they lose that and they begin to open up. And so they begin to cool at around, and this seems to be around 38 degrees C. I mean, that needs to be looked into, because what I've tried to point out is these high VPDs coincide with droughts. So the stomata are already responding to a soil moisture stress. I don't know how much more this trait, how this might interact with what we know is already going on. But that was interesting, that there began to be recognition that this could be a potentially serious issue here. So that's just a very brief and very kind of cursory overview of what we're doing. And we hope to be able to continue this work, particularly extend the statistical modeling to include other regions, and also do more work on our eddy covariance and crop growth modeling, looking more into these interactions between the climate and the crop. I want to acknowledge the group I mentioned before and these other folks for all the work, all the input that they provided for us. In particular, Andy Schweiker at Mead for the Meriflux data, Paul Stokowski and staff at Musgrave for the Flux Tower, a couple of folks at Pioneer for information on their cultivars, and Tim for some helpful discussions. And that's our Flux Tower from last year at Aurora. So thanks.
Thanks, Jeff. Just a quick question on the drought-tolerant variety yields. I don't know if you can look back at that slide. The units look like maybe kilograms of yield, or then up to 700. I'm sorry, towards the end, the drought. This is what you see.
Yeah, they're in grams per meter squared, so you multiply that.
Yes.
Yeah. How we should interpret those context trials. And so because the farmer enters the contest at the beginning of the season, are they permitted to withdraw? For example, maybe it doesn't look good and they don't want to have it on the record, so they withdraw.
Well, I believe that they can drop. I don't believe that they're obligated. I think, again, we are looking at the best sites. That's a good point. As far as I know, they're not obligated. It's like they haven't kept up with. We did find quite low yields in the rain, so it's not like they're saying we don't get 10 metric tons. But yeah, that's a possibility. But it's important to keep in mind these are the best sites, so those yields are high.
You can explain this, but my understanding as a soil scientist, not too much of a crops person, was that the key yield determining factor around drought and corn was basically around tasseling and so on. And so when I look at that top graph, if you are, the drought cuts off the top crop basically by shutting down the stone maize, doesn't it sort of increase then the effects of the drought? I'm surprised that you get higher yields when you increase the stress during the critical time, or am I getting it wrong?
Well, so do you increase the stress during the critical time? I think the reading is such that, and I didn't show this graph, but the reading is such that the varieties that show this are still performing well under both well water and drought conditions. If the response was so great that you were shutting down photosynthesis, then you would expect it. I don't think we're talking about a big difference. We're not talking about, because this is occurring at BPDs that are above about 2 kPm. So it's not like we're talking on the order of 30 millimeters of water. So it's not imposing. I don't know if I'm answering this, but it's not. I don't think it's a significant stress, and not during that critical period. If it was a very significant loss, it was very strong reductions. But it's
I mean, in that graph that you showed, some model conductance in 2012, at every hour of the day, it was lower. So, remember those box plots? So it could be that if you prevent the onset of drought by allowing the plant to regulate, that then it would, then you would just have normal conductance. Those plots would have been shifted toward the normal areas throughout the times of the day when it's not usually.
Yeah, well, I mean, that was water stress was causing that. So that, I didn't show this, but what's interesting about that is that if you look at the carbon exchange, it actually wasn't all that much impact. They were pretty similar on all 3 years. And in fact, the yields that they got in all those figures were not that much different. They were pretty close. So even though it showed this response in 2012 that it clearly not keeping up and we had lower crop conductances, it didn't actually end up impacting yield. So that was interesting.
Go back to the slide that shows the effective big pressure deficit at different planting densities.
Yeah.
I mean, just to say that it was counterintuitive to me, and I wonder if you can give an explanation. So in other words, it shows that at low planting density, the yield suffers more as VPD goes up than at high planting density. And
I know it doesn't. Yeah. But I think what we're looking at is the quality of the sites. So I think in these sites, we're not seeing as much. you notice with the yields were quite high for rainfed. We're familiar with yields in the Midwest, of, 14 or 15 metric tons, that's pretty high. So I think we're talking about really good size. So it's important to keep that in mind when we're talking about these yield. So actually these rates were too low. They were losing yield because they were not getting enough plants out for the optimum density for those conditions. So they could put more plants in there. They were below the optimum for density for getting the maximum yields. You wouldn't think that would be the case, but it was. I mean, at any given BPD, yields go down. At any given planting density, yields go down as you increase BPD.
Well, not much at 100,000.
No, not much. No.
So in other words, the plants at 100,000, they're maintaining the per plant yields even as BPD doubles.
Yeah.
It seems amazing to me.
Yeah. Well, that's again, my interpretation of that is your yield contest.
Okay.
So that's what I'm. This was
So
driving.
some of this correlation or relationship is driven by non-independence between planting density and the location.
Yeah.
People with really good soils, they plant at really high density, and yeah.
But also, the lower densities were more in the western part of the Corn Belt.
Yeah, we
They
had,
were.
there
Where there were
some
higher BPD.
spatial gradients
Yeah.
with planting density.
Yeah.
Could you also say that at low planting densities, if the plants are not under VPD stress, they can kind of compensate, but if they are under VPD stress, they can't compensate for the low density? Does that make sense? Never mind, it's fine. Forget it.
The other thing,
Maybe we need to cover back to evaporation, just water loss that's not intercepted by the canopy. Okay, that's probably, I don't know.
Actually, we're looking at the whole issue of lower planting densities and how much water you actually save by doing that. That's something that Liz is. Okay, thanks.
This has been a production of Cornell University, on the web at cornell.edu.